In this section, we're talking about modeling beams in Ansys. We'll show you how to create the beams in Space Claim, how to extract the shear moment diagrams, and some thoughts on understanding beam outputs. These can provide a way to analyze more complicated cases than you can use with beam tables, though as you'll probably see, they can often take a little bit more time than just doing a calculation from the beam table. But once you understand the relationship between those two, and you'll do that by applying it to one or more of your homework problems this week rather than doing a full lab and analysis. But let's take a look. What I'm going to do is show you with this example problem. This is solved out completely in the notes for reference. This is problem 383 in the textbook. And you can see that we've got a shaft with bearings on each end, and we have and then pulleys in the middle that are applying torques between A and B. So when we're analyzing this by hand, what we could do is do three body diagrams. Since we know these forces, magnitudes here, and we know the ratio of T1 and T2, I can write the moments about the x-axis and solve for T1 and then T2. So I have, given these relations, I have two relationships and two unknowns. The two relationships being T2 is 15% of T1. Then if I'm solving that, I would write the two separate free body diagrams, one in the XY plane, as you see there. And so we have forces from the pulley that are going up at 45 degrees. So I have that net force, and I can solve for the reactions in the Y direction. And then I can do the same thing in the Z, where I have reactions from both pulleys, as illustrated. Now, to model this in Ansys, what we could do with a beam is basically just a line. So we would have a line there, though we need to be able to have nodes where the two pulleys are to be able to attach us. So this here would be O. We'd have location A, location B, and location C. Here we have we're going to model this as a simply supported beam. So we need to constrain the reactions, but not rotation, reaction forces, but not rotations, and we'll constrain just one location. I'm going to choose O to constrain the x-axis. At A and B, we will put the combined loads. So we have 345 newtons at 45 degrees. And at B, we solved for that. That was 287.5 newtons. And then those are the beam loads. But if we also want to do the account for the torsion on here, and we'll talk a little bit about this, we would also put a moment on here. So we'll put the moment related to that one, and then we'd have a moment, negative moment from the other torque. And we'll put that. So we'll show you how we'll create that in SolidWorks now. Sorry, in Workbench. All right, so again, we come to our standard case. We're going to create a static structural analysis, drag and drop that, or double click on it. This time in the geometry, we're going to use one of Ansys's geometry creation tools. You can see there are three of them here. They each have their strengths. All of them are a little bit difficult to learn, but we're going to focus on space claim for this purposes. So I'm going to create new space claim geometry and give that a second to open. Okay, so here we are in the space claim interface. So we can see we have a plane driven here. It's defaulted to the XZ plane. We are going to, we can orient normal to that. I can also, again, I can use the middle mouse piece to rotate. If I select this, I select a new sketch plane, and so it's kind of defaulting to one of the three planes of the coordinate system. And I'm going to choose the XY, and then I'm going to click here to get a plan view to that. That tends to just play well with some of the Ansys defaults if we draw in the XY plane, particularly if I end up doing 2D analysis. In this case, this also lines us up really well for drawing our shaft since it's along the x-axis. So to draw the shaft, we're going to represent this as just a line. So I can select my line tool up here, and I will start for convenience at the origin. I'll click, it'll default there. Now you can see that it's given me a distance. I could just click, it's snapping to standard distances. And while it's highlighted, I could just type a value in there. So the length of the first section is 300 millimeters. So I'm going to just type in 300, enter. You can see that it'll create that bar. Now I can come out there again. Again, it's straight and parallel, so I can select this, keep it in line with that, and I'll just do 400, enter. And then again, the last one is 150. So this is very, very simple. There'll be some other videos we could show you for learning to draw other things, but this will get you most of your beams, right? So now I'm going to hit escape twice. So it's gone back to the select tool. And you can see if I highlight this, I have 3 elements there. Now, this has a really, very easy way of creating beams. So what we're going to do is we go to the Prepare tab and we see the profiles. And so I want to create a beam profile, and there's some standard profiles that I can use. And here we need a solid circle, so I'll select a solid circle. You could select more than one, but we only need the one. Click down here. So I come over here to this Layout tab. I can select it. You can see that it gives some default properties. If I right-click on it, I can edit the beam profile. Now, one of the nice things is this is parameterized. So if I click on this, you see it says 10 millimeters, which happens to be perfect because the problem specifies a 20 millimeter diameter. So I'm not going to change that here, but you could click on it and change the value if you needed to. Now at this point, you'll notice if you come down to the bottom, we see the circle and we see our design. So we've got 2 different tabs. I want to go back to the design so I can see the overstructure. And you may find like this one that it's changed what you're looking at. What I'd like to see is the design tree. So I can click on the structure tab. And I can expand these out, and I can see I have these 3 lines. Again, under the Prepare tab, now I have the Create option, which would create a beam. And if I had an edge of a model, other things, I could select those, but I'm going to use the lines. So hit Create, and if I click on that, you notice that that blue line disappeared, and we can now see that it's a beam. We'll click again, and it's created 3 beams. It still has these lines in here, and this is an important point. If it still has them, it's going to try to analyze with those as well, and could get confused. And so if I right-click on the sketching plane, I can put Suppress for Physics. So physics means simulation. So this means that it will not bring that into Workbench. If you leave it in there, you will get errors that say that it is sufficiently constrained, because you'll have these additional lines without that aren't beams, that aren't constrained. Now, I have my 3 beams here, and I want to select these, right-click those, and I'm going to move those. This is not highlighting well. I don't know what's going on here, but right-click, move to New Component. And I'll name this, I'll just call it Shaft. Okay, so now all the shafts are in there. What this does is it lets me connect it until these are one part. And I can tell it about if I click on the shaft, I have the shear topology, and I have a selection here. What I want to do is to share those. So that means that the nodes at the endpoints, it's going to say they're continuous. So if one node moves or if their angle changes, it has to be continuous across the beams, which would be basically saying it's one element. Now I could go ahead and save this, though it should save inside the project. I'm going to leave that for now. Let's come back to Workbench, and let me save the project. And we'll just call this 383 3 demo. So I save the model, and then I can, again, as before, I can double click on the model tab and open that up to be able to start Ansys Mechanical. So I'll do that now. Okay, so Ansys Mechanical is now open. We can see we have a single line in there. If we go down our tabs, we see Geometry Imports. We click to Geometry, we can see we have a beam with a circle shape. Materials, it's default to structural steel. You know how to change those results. We won't focus on that today. Cross section is defined. You can see my radius is in there, and it calculated the section properties that are associated with that. Let's come down to mesh and just generate the default mesh. This is one case where the meshes usually are fine. Let's see. So I could hit display on my mesh, and you can see that it's showing it as a series of lines or circular segments. This helps you visualize it. Inside, it's really just line segments with the multiple degrees of freedom, but it helps you see that these are beam elements. Now, if I keep coming down here, I'll notice I need to define my analysis. So I need to set my boundary conditions. There are a few things that I could use to do this, but I'm going to suggest that let's go back to our environmental context menu, and let's do remote displacement. Okay, so we'll select this vertex, apply it, and we can set any of the 6 degrees of freedom with the remote displacement. So in this case, we said that this was the fixed position. So we're going to fix each of these axes, X, Y, and Z, but we'll leave the rotations open. Now let's add another remote displacement. Sorry, supports, remote displacement, and we'll select the other end for the other bearing. Now this one, it's simply supported, so I need to leave the X free, put the Y 0, Z 0. Interesting test would be to fix that and then simulate a change in temperature, but we won't do that at the moment. All right, so you can see I can highlight these, and I have boundaries in here. Oops, you know what? I selected the wrong point. So let me come back to this remote displacement and apply it all the way at the end. Apply there. Oh, so I selected the edge. I don't want the edge, I want the end, and apply. So remote displacements can be applied to a variety of things, and it constrains it to just 1 degree of freedom. Okay, so we fixed those two, so we have our bearings in place. Now we need to put on the boundary conditions for the shafts. So we'll select a force, select the vertex, apply. This is going to be easiest to do with a components. So we have a Y and negative Z here that are 345 times basically sine cosine of 45 degrees. So that would be 243.95. We could call that, I think it's positive Y and a negative Z. Right? And I can kind of look at that, and you can see it draws the vector in the next direction. Now I need to add a force to for the second pulley, and we already solved for that with the free body diagrams. I'll again select the components. This is in the positive Z direction, and the combined of the two sides is 287.5 newtons. Now, if I try to solve this, let's see what it says. So you see, not enough constraints appear to be provided. What would be unconstrained in this analysis? If we think about this, I've applied moments, but I've applied forces, but I haven't constrained rotations about the x-axis. And we can see that it has a pivot error in the x degree of freedom. So That's telling me that that's probably where the constraint is. Now, what I could do is apply apply a support in there to stop rotation. So let's, and I'm going to again just do that with a remote displacement. And I'm going to pick one of these nodes where we have the shaft, or at location B. Apply that, and rotation X, set equal to 0. I'll also go ahead and apply the moment at location position A. So apply that, and select our components around the x-axis, and that is 31.875, if I remember right, Newton meters, about the positive x-axis. So now let's see if that will solve better. Invalid geometry. Lovely. Let's see what we've got. So I should have noticed this. I got a question mark here, and I have a fixed support that I didn't assign any, I accidentally created. So I'm just going to delete that. Let's try solving it now. Okay, now it's still giving me a warning. Let's see if it solves successfully. Sometimes it does. I think it should be right. Sometimes it has troubles checking that whether there's sufficient, but it does still have sufficient constraints. And we see here that it did solve successfully with the green X. Now, we need to add some displays here. Now, if I were to come up under strain or stress, you see that these are all hidden. And that's because these plots don't extract information from beam elements properly. So there's two ways I could go. The toolbox, I can add a beam tool, and you can see that gives me stress, minimum combined stress, maximum combined stress. I can also insert deformation. We'll add a total, and we'll go ahead and add a deformation directional. I'll duplicate that. So directional deformation, we could look at deformations in the Y and deformations in the Z separately. And let me rename these so we could have, I didn't know you could do that. It automatically did on that. That's really convenient. So you see how it renamed it based on what I defined it as. Right. Now there's another spot I can get information. If I come up this about beams, so solution, we see this beam results diagram. So I could add in axial force, bending moment, torsional moment, shear force, and shear moment diagram. We'll get the works. Okay. Now the shear moment diagram needs a definition, and so I actually has to define a path. So I come to the model. There's not a path heading by default, but if I hit insert, construction geometry, path. A path allows it to extract data along particular points. It's going to default 2 points. I'm going to try edges and select my beams. Now this is what's going to allow you, so let's apply that geometry selection, and let's name the path entire shaft, we'll call it. When I come down here to my shear moment diagram, it's asking for a path, and I'll see a drop down. I can select entire shaft, and now it's happy, it's defined. So let's extract the data for all of those plots, and we can see now that I have the shear moment diagram that in fact draws the shear moment diagram for me. and it's doing the total shear force, total bending moment, and then total displacement. I can actually see, let's duplicate this. And if we come in, I can select a, rather than total, I can do directional. So YZ, and let's do a ib, and I could similarly change some of these others too. But let's go ahead and retrieve the results, evaluate all results. And you can see I can now have them in just particular planes, the YZ. So the Y, Z shear force, Y bending moment. Looks like I've got a mix of different values in there. But this allows you to get results that you could compare to your hand calculations if you solve this as two-dimensional problems. A couple other things we'd see. We could see a plot of the shear force, and it goes in jumps, which matches what we expect from the shear moment diagram. We can see our torsional moment. You can see it's 0 at the ends and it's high in the middle, which is what we expect. And we can see what our bending moment does. And you can see you could also do directional bending moments here if you wanted to compare that. And axial force, which is 0 because we haven't really applied anything in this case. So we plot the stresses that result from that, the total deformation, and we have Y and Z axis deformation. So you can see how you can get the results out to be able to compare to your hand calculations, the things that you'd get from there. Okay, so a couple things that you might be interested in trying. You could go back to space claim and try changing these dimensions. Actually, we could change it right here. So if we were to put it 0.012 millimeters, I could resolve that and see what happens to my stresses. So working on it. So I've actually combined stresses. You can see that the stresses go down. We didn't really, it was around 52 megapascals before, went down to 31. All right, let's take a quick look at what happens if we were to over-constrain our bearing mounts and fix both of them along the axis in the x direction. So in order to do that, we're going to go ahead and I'm just going to duplicate this analysis. I created a second one here. If we were to go back to the Workbench tab, we see that we have a new one that's connected there. It's just a different way of creating that. We did it before from the Workbench project view. But here we can do it in mechanical view. So I have my original analysis, and for this new analysis, and let me just rename this. Let's see, so over-constrained in X, we'll call it. We'll rename this one constraint X, so simply supported. Right. So to get that over constraint, let me expand this out. We'll go back to remote displacement. Instead of setting the X component free, we'll set that equal to 0. Now I'm going to go ahead and insert. So that's all fine as long as everything's perfect. And so if we were to, let's go ahead and show that. Let me just solve that. And we will compare the axial force, which here you can see in the original, 10 to the minus 11th pascals, right? Newtons, right? So this is just negligible calculation noise. And we'll compare that to the case where we have it over constrained, and we see that it's a little different numbers, but it didn't change it substantially. It's still 10 to the minus 11th. Now, what happens is the error comes when things don't fit together perfectly. So it might be a little tight, or the dimensions might be off. One way we could see that, though, would be to add a temperature change. So we put a load, let's put a thermal condition on there. Now I need to tell it where to apply that thermal condition. So let me come over here to my mode. Normally we've been on single select, so I could select individual elements. Okay, so it's scoping it to the body. We could have also done a box select and selected that. Now, this is the default temperature, and so nothing really changes. But watch what happens if I say, well, maybe this is running, it's a little bit hot in here, and it heats up to 45 degrees C. And now let's just go ahead and solve this case. I'll right-click Solve, and we'll take just a second while it calculates, and we'll take a look at what happens with the forces. So we have axial force. Now we see that we have 17,000 newtons of force in there from the fact that it's trying to expand axially from the temperature change. A fairly modest change, right? 20 degrees C. That might happen in a hot working environment with things spinning, and 17,000 newtons of force were created that will. And in practice, that might actually buckle the shaft. This analysis isn't going to account for that, but it could be quite substantial. Now, one of the things I want to point out is if we go to the stress, so we have the combined stress, that increased. Now you see that it's negative here to more negative. Also notice that it doesn't show you the stress and tensile sides of the bar. That's why I have separate plots for minimum and maximum. However, these stress plots do not account for the torsional moment that's here in the middle. This only includes axial, direct shear, and bending stresses. And so that's important to recognize when you're looking at these plots. Okay, so that's helps illustrate a couple points. Hopefully, it helps you to see how you could do one for your homework. You'll apply this to problem 3-81.